Hello, I'm Alessandro Pegoraro, and here I will present you DeepEclipse, how to break white box watermarking schemes for white box watermarking. So let's start with some information that you should all know. Why do we use watermark to watermark our work? Usually it's to distribute a product, maintain proof of ownership, and usually we embed either a visible watermark or a hidden watermark so that the user can see and know who is the real owner. And now, I will ask you, why you should train a model? Let's start taking an example, for example, ChatGPT-3. To train ChatGPT-3, I would need 20,000 NVIDIA GPUs with 32 GB of memory. I would need 45 terabytes of labeled text data, and we all know that people do not want to label data for free. On the same page, I would ask you, could you help me label this data? No one? Then I suppose I will have to spend $4 to $12 million to train my ChatGPT-3 and then distribute it for free, giving you access as it is being distributed by OpenAI. So the real question is not why you should train an AI model, is why you should steal an AI model. Obviously, I know that no one of you wouldn't download a neural network. So what are the solutions? A solution is watermarking neural network. There are two main branches of watermarking neural network. Both of them assume a judge, an impartial judge that follows a protocol, for example, from a paper proposed here at USENIX. And there is always a neural network that we want to know if it has been stolen or not. The first case is black box watermarking, where the judge has no access to the stolen model and tries to analyze the behavior. So how can it analyze the behavior? With input and output. So how can a judge analyze if a model has been stolen? A simple example is I put a vector on my input and checks the output. If the vector is ignored, I can say probably the model has been trained by someone else and it has not been stolen. But if the model misclassifies, then it's probably been stolen because it is some behavior that the original owner has imprinted into the model. This black box watermarking usually is not really secure, in our opinion, because the misclassification could have been also imprinted by the original, by the other owner. So you need a lot of data to test and a lot of inquiry to the model. The other watermarking approach is white box watermarking. In this case, the judge has a secret key, usually a bit string. And again, there is a model that we want to know if it has been stolen or not. This time, the judge has full access to the stolen model and can therefore inspect it and extract a key. We then compare the two keys. If they are different, then the model has been trained by someone else, not has been stolen. If they are similar or identical, then the model has been stolen. This approach, we consider it more rigorous because the probability of collusion is 1 over the length of the key, over 2 to the power of the length of the key. So all of these approach for white box watermarking that we will also tackle in our work. Are there been any other watermarking removal attacks proposed? Yes. For example, we have watermarking overwriting, in which I inject another key of the same type, such that when I extract a key, when the judge extracts a key, it doesn't know if the key is the original owner or of the adversary that has injected it. As it has been said before, distillation, I will use the original model as a teacher model to train a smaller model, student model. Fine-tuning, we all know what it is. We try to retrain the model to change the weights. And then weight pruning, in which some weights are put to 0 or removed in the hope to remove the watermarking. But what are the limitations of these approaches? They need to have some knowledge of the watermarking. For example, watermarking overwriting needs to know which type of watermarking has been injected to inject the same watermarking. They need training capabilities for distillation and fine-tuning. We need to know, we need to be able to train the model and also have availability of data. So let's look more in depth how the white box watermarking works. We have a model that is a sequence of layers. Then we have the input that is passed through each layer, and then it's multiplied by each layer. And we have obtained the output. So it is a simple matrix multiplication plus bias. How can a defender inject a watermark in this scenario? It can either put some specific weight of the layer to some value that is secret key, or it can put some specific weight on the output of the multiplication, forcing the multiplication to always return a range of value or some specific value. But we ask ourselves, is the signature really hidden? In our work, we analyze the trends and patterns in the layer weights using the simple moving average of the discrete Fourier transform of all the layers' weight. And we observe that due to the restriction that we discussed before, to force the layer to have some specific value, usually the watermarking embedder uses some regularization. And that regularization is easily spottable. You can easily spot, and that helps us now to detect which layer can be could have been watermarked. So now, with this information, how to break watermarking? We could change the weight of the layer to some random layer to change it to change the encrypted key, but then we will have unexpected behavior. Obviously, a model with random weights is a model that has not been trained, and we have a drop in accuracy in utility. We could change the shape of the layer such that the position of the specific weight would not be the same, so the impartial judge, sorry, so the impartial judge could no longer find the specific weight. But neural network obviously follow a strict matrix multiplication rule, and then there will be this dimensional compatibility problem during the multiplication of the input. So our solution, obfuscation. We want to split the layer using the identity matrix. The identity matrix has this common property that whatever is multiplied by the identity matrix returns itself. So for example, we know that the yellow layer has been watermarked. We split the layer into two layers that maintain the same output and the same behavior. So how would a simple pipeline of this work? First, we find a random matrix compatible with the layer we want to change. Then we multiply that matrix with the original layer weights, and then we calculate the inverse of the new matrix. But is calculating the inverse of the new matrix that easy? Let's ask ChatGPT. Can I calculate the inverse of any matrix? No. Only square matrices with a non-zero determinant have an inverse. Sadly, most of the model layers are non-square matrices. Now, would come to surprise you, but ChatGPT is lying. It is possible to calculate the inverse of a model of a rectangular matrix. How do we do it? First, we need to generate a rectangular matrix with full rank. Then we calculate the transpose of that matrix. That is pretty easy to do. Then, for the property of the inverse, if we multiply a matrix by its transpose, we will obtain a square matrix. And as ChatGPT has told us, we can calculate the inverse of that. Then we can simply apply the associative property and obtain H, the inverse of H. So how would this apply to our approach? We have, again, our watermarked layer. We extract it. We multiply by H. We multiply by H minus 1, and we obtain again back the original watermarked layer. So we can split the layer how many times we want. So we could also split H minus 1 how many times we want to further obfuscate the model. Now, this brings a problem, as I said before. When the signature is, when the white box watermarking signature is the output of the layer. If, as we claimed before, we maintain the behavior of the original layer, the output should remain the same or similar. So the secret key will still be present. How do we solve this? We will have a little drop in accuracy, but we can split contiguous layer into 3 layers. So we will have again this watermarked layer, and non-watermarked layer, or again a watermarked layer, and those two will have been split into 3. That again maintain the similar behavior to the original one, because again it's only matrix multiplication. So, in the end, we find that obfuscation is a viable watermarking attack, which does not need available data, training resources, or knowledge of the watermark it applied. With the proposed DeepEclipse, which maintain the behavior of the stolen model, incurs minimal drop in utility, and target common watermarked layers such as linear layer and convolutional layer. This approach is not applicable to behavioral watermarking, such as black box or similar. And also first probing, first probing shows that it's effective also against watermarking of large language model that tries to watermark the encoder-decoder portion. Thank you. Any question?